has found comfort in its presence. It's been a beacon for nocturnal travelers, a timekeeper for farmers, and a location finder for sailors at sea. For some cultures, it's even been a god. It's the only cosmic body ever visited by human beings, and today, NASA is planning a permanent outpost there. But how did it get there in the first place? How did the moon come to be? The answer is more astounding and spectacular than most residents of Earth have ever imagined. At last count, over 150 moons populate our solar system. Neptune claims 13 of them. Saturn has 48. And Jupiter hosts an astounding 62. Earth, on the other hand, has just one. But it's a special one. Our moon, Luna, as the Romans named it, is remarkable in its size. It is by no means the largest moon in the solar system. Several others are bigger. One of Saturn's moons, Titan, for instance, is twice the size. But our moon is the largest in relation to its host planet.
It's a quarter the size of the Earth. It's really big compared to the Earth. If you look through a telescope at the Earth from a distance, you'd see the Earth and this other big thing. If you look at Jupiter or any other planet, you got the big planet and then little tiny moons right next to it. So our moon is so much bigger, and it's the only one of the now 8 planets that has that situation.
The relative sizes of the two bodies are close enough that some astronomers go so far as to refer to the Earth-Moon system as a double planet. The mean distance from the Earth to the Moon is 234,000 miles, a 3-day flight through space. Luna's diameter is roughly 1/4 the size of Earth's, measuring 2,160 miles. A single day on the Moon is the equivalent of 27.3 Earth days. This is because one side of the Moon permanently faces us. Luna is phase-locked with our planet. So the Moon must fully orbit the Earth in order to make one complete rotation on its axis. Sort of like children in a game of Ring Around the Rosie. They always face inward as they hold hands and move in a circle. Yet as closely related as the Moon is to our Earth, it would only take a brief visit to Luna to make it quite clear that it is in fact a very different world from our planet. And an exceedingly dangerous place.
Tranquility Base here. The Eagle has landed.
There's no air, of course, so you need your spacesuit.
Indeed, the Moon has absolutely no atmosphere at all. So there is nothing to carry sound waves. If you were standing on the Moon with a friend and tried to converse, the person wouldn't be able to hear you, except by radio.
I was strolling on the Moon one day in the merry, merry month of December.
No atmosphere also means that there are no air molecules to scatter light from the sun. So the sky is always black. And the landscape does little to help brighten the scene.
Kind of monochromatic, you know, not much color there. The rocks are mostly gray-brown colors. It's maybe a little warmer tone in one direction, maybe toward the sun, and cooler tones, grayer tones looking in other directions, but not so colorful.
Extreme temperatures would also add to the unpleasantness of a visit. The swings between hot and cold are brutal, from 270 degrees above zero at midday to 240 degrees below zero at night. Even the moon's low gravity, just 1/6 of Earth's, could present a hazard to a tourist. A reality the Apollo astronauts kept at the tops of their minds during their many moonwalks.
But they realized that beyond the thickness of their visor in their spacesuit was death. Should they do something and fall into a rock and lose their footing and fall and hit an outcrop, this visor could be cracked, exposed to the lunar vacuum. We would have had a serious situation on our hands.
But while a spacesuit could protect lunar tourists against the vacuum of space, a lack of oxygen, temperature extremes, and lethal solar radiation, a potential hazard a spacesuit would do little to protect against is high-velocity micrometeorites. They pummel the lunar surface frequently.
Tiny meteorites, the little ones that burn up in our atmosphere and make shooting stars, there's no atmosphere on the moon, they're coming right down, hitting the surface.
They pulverize the lunar surface, generating a dusty blanket of gravel-like material called regolith. Dr. Amanda Hendricks studies the moon at NASA's Jet Propulsion Laboratory.
This plant here is kind of a regolith factory. It's ground up rock, is what it is. The timescales at this gravel mill are a lot faster. Here, it's made in less than an hour. But on the moon, it is the result of more than 4 billion years of bombardment by meteoroids and micrometeoroids raining in on the surface and breaking up the rock.
Like the product of this gravel mill, lunar regolith has formed in a variety of grain sizes, from large rocks to fine dust.
This very fine dust is familiar to us from Apollo images that were seen of astronauts' footprints in the dust. It's very fine, and so fine, in fact, that the astronauts had problems with it sticking to their spacesuits, getting into the equipment, and it can end up causing a bit of a problem.
Really big meteorites have also hit the moon in the past. In fact, these massive impacts are responsible for the dark circular regions on the lunar surface, the shapes that to many observers seem to be arranged like the eyes, nose, and mouth of a human face. They make up the illusion of the man on the moon. They blasted huge basins in the moon's surface. Some of them are 700 miles across. Dark lava eventually burst through at the impact points and flooded the basins. Today, we call these dark regions Maria, the Latin word for seas. This dates back to the 17th century when Renaissance-era observers looked up at the moon. They speculated that the dark areas might be oceans, and astronomers of the time gave the many dark spots, or seas, whimsical names.
The seas are all named after effects that were once attributed to the moon. So you have the Sea of Storms, and the Sea of Crises, and the Sea of Tranquility, and so forth.
Some of the younger impact basins have had less time to erode, so their features are still relatively crisp. One in particular is called Mare Orientale, or the Eastern Sea. It's some 600 miles across, and the impact that created it was so massive and direct, the result looks very much like the bullseye on a target.
This Orientale scar is kind of like a bullet shot into glass, where you see all the sort of rings around it and fractures going out. People have often said if that had been on the side facing directly toward the Earth, we might have had a whole different mythology about the moon, because it would have looked like a big eye staring at us.
Three concentric rings of mountain ranges surround Mare Orientale, and some of the peaks rise to several thousand feet. They're all effects of the monster impact.
When we see mountain ranges on the Earth, they're mostly caused first by the continents moving around, crashing into each other very slowly, buckling up and creating mountain ranges, which then erode into all the spectacular shapes that we see, the Matterhorn and so forth, from water erosion.
On the moon, there are no continental plate tectonics. The surface is static.
Yet you still have mountains on the moon. And the reason is that those big impact basins, that's a big explosion, excavates a pit, throws material up on the outside. So you have these rings of mountains, arcs of mountains that surround the impact sites. But they're impact features. Again, they're caused by the external forces, not the internal forces.
Another notable impact crater, much smaller than Mare Orientale, but every bit as spectacular, is Tycho. Named after a prominent 17th century Danish astronomer, this impact feature is located in the southwestern quadrant of the moon's near side.
It's in the bright area. You can almost see it with your naked eye. And when that explosion happened, as with many other craters, it shot out jets of bright, powdery dust. So there are these rays that go out from it, and it's very striking.
The rays of dusty, ejected material extend some 900 miles from the Tycho impact site. A mountain of debris also rises from the center of the crater. This is a result of recoil from the asteroid strike. Some of the highly compressed material at the center of the impact site springs outward once the impacting body either ricochets or disintegrates. But long before any of the moon's specific features could be discerned through sophisticated telescopes and space travel, careful observation of lunar behavior and appearance was still vitally important to Earth dwellers. For 15,000 years at least, man revered the moon as a source of light, as a navigational guide, as a reference in agricultural pursuits, and most of all, as a convenient timekeeper. In the days before our modern systems, timekeeping was no simple task. Early timekeepers had two choices. They could monitor the sun or the moon.
If you think about trying to keep track of dates, If you use a solar calendar like we do nowadays, there are 365 days in a year, and that's an awful lot of days to keep track of. And it's not something that the ordinary person can do very well. Compare that with a lunar calendar. Everybody can tell when the full moon is, when the new moon is. You don't see the moon at new moon. You see it, it's big and round at full moon, so it's easy to tell. There are only 28 to 29 days in a lunar cycle, so it's easy to count them. And so most societies actually start out with a lunar calendar.
Early observers of the moon also recognized that our planetary neighbor has a very real physical effect on the Earth itself. The moon is responsible for the rise and fall of our ocean tides.
If we think of the moon as being this tennis ball and the Earth as being this football, okay, the tides are caused by the moon's gravitational attraction. So it's obvious, okay, so the moon kind of pulls the Earth's water towards it. And so this creates a slight bulge in the direction of the moon. What's less obvious is there's also a bulge in the direction away from the moon. So there's in fact 2 high tides every day. The other high tide you can think of as being caused by the Earth's centripetal force. The Earth and the moon are both rotating around, and that causes the water on the far side to also move out.
An extreme illustration of the difference between high and low tides can be found along the shore of Canada's Bay of Fundy. The water level from high tide to low tide drops an astounding 55 feet. For some forms of life on Earth, the advance and retreat of the tides creates useful habitats. But another of the moon's gravitational effects on our planet is directly responsible for nothing less than the continued survival of terrestrial life itself. The moon stabilizes Earth's climate. The gravitational effect of the moon keeps the degree of tilt in the Earth's rotational axis constant. This tilt is what maintains the repeatable cycle of seasons as the Earth orbits the sun. Over the millennia, with the moon's prominent and constant presence in our night sky, men ultimately began to speculate on its origin. How did it form? How did the moon come to be? In 455 BCE, the Greek scholar Anaxagoras theorized that the moon was simply a rock that was flung off by the Earth. Most of his contemporaries, on the other hand, were convinced that the moon was a god, or maybe a huge ball of fire. So Anaxagoras' notion did not get much traction. Quiet speculation no doubt continued, but no hard information about the moon came until 1609. When Italian astronomer Galileo Galilei pointed one of the first telescopes at the moon and recognized that he was looking at a landscape, the terrain of another world.
When you look at the moon through a telescope, it looks completely different from the way it looks to the naked eye. Instead of looking flat the way it does to the naked eye, it really looks round, and you can see the shadows, you can see all these craters that the naked eye does not see, and it just immediately looks like a world. It jumps out at you into 3 dimensions.
Galileo made detailed drawings of the small planet's surface and established once and for all that the moon is a solid world, not a god or a fireball. But the groundbreaking astronomer never publicly speculated on the moon's origin, primarily because his interests soon moved to other planets. Not until 1873 did the first science-based theory regarding the origin of the moon publicly emerge. It sprang from the mind of a talented French astronomer named Edward Roche.
Roche advocated what's called the co-accretion theory. which says that basically Earth and the moon grew up at the same time out of the same materials.
In Roche's day, many scientists began to believe that the planets might have formed from hot condensing clouds of gas.
It gradually contracted and cooled, and as it contracted, it would separate out rings of gas. So you'd have a ring of gas here, a ring here, and so forth. And these rings of gas would then eventually coalesce and form the planets. Roche saw the Earth and the Moon as a solar system in miniature. His idea was that the Earth starts out as a ball of gas and then cools and contracts and sheds a ring of gas that then itself coalesces and forms the moon.
But there are problems with this theory. For one, our moon has a much lower iron content than the Earth. If the two bodies formed from the same materials, their basic composition should be the same, but they are not. This and other inconsistencies soon led fellow astronomers to quest for new ideas to explain the existence of the moon. In the last third of the 19th century, advanced theories about the origin of the moon started to emerge. In 1873, French scientist Edward Roche proposed that the moon simply formed alongside the Earth out of essentially the same nebular cloud of particles and gases. But this idea had a fundamental weakness. The moon has a much lower iron content than the Earth. It's much less dense.
The big thing to remember about the moon and its composition is that it doesn't have any iron core like the Earth does. So you look at the Earth, and there's a very large central area, something like half the inside of the Earth is iron, nickel iron. And that's metal that drained down to the center of the Earth when the Earth was hot, when it formed at the beginning. The moon is more like just plain rock.
Scientists initially deduced the mass of the moon through observation and mathematical calculations. If the moon had formed from the same stuff that made the Earth, the iron content should be similar. It was a hole in the theory Edward Roche couldn't explain. But another idea soon followed on the heels of the co-accretion hypothesis. In 1878, George Darwin announced his fission theory of lunar origin. This idea received some attention in part because Darwin had a celebrated father. Charles Darwin, author of Origin of Species. In time, though, George Darwin stepped out of his father's shadow and became known as England's leading expert on tides. And through extensive analysis of the tide-moon relationship, George Darwin came to the realization that the moon is gradually moving farther and farther away from the Earth.
It wasn't proved until 95 years later when astronauts landed on the moon. They put little mirrors on the moon. And you can shine a laser at the moon, and the laser will bounce off the mirror, come back, and you can actually measure the exact distance between the Earth and the moon. And the rate at which the distance is increasing is 3.8 centimeters per year.
3.8 centimeters is about 1.5 inches.
If you made a movie, extreme time-lapse, you would see the moon moving away from Earth gradually. That's what we see nowadays.
Darwin began to consider what would happen if you reversed the process, if you ran the movie backwards. As we move backwards in time and the moon moves closer, both the moon's orbit and the rotation of the Earth get faster and faster.
And so, well, what happens is that eventually the moon must coalesce with the Earth. It must hit the Earth.
The logical conclusion for Darwin was that a portion of the molten, rapidly spinning Earth must have separated from the main mass and spun off to become our moon. He immediately began work on mathematical calculations to reverse the trajectory of the moon all the way back to the Earth.
Frustratingly, he reaches a point where it gets almost to Earth, and then he couldn't work it out any farther. The mathematics doesn't let you go any farther. What you get to is a point where the moon is whipping around the Earth at a rate of 5 revolutions a day, or 6 revolutions a day. So it's just zooming around the Earth. Okay? And it's about 5,000 miles away from the Earth.
Still, the mathematics did not allow Darwin to bring the two cosmic bodies into contact. The fission theory was debated for decades, but scientists eventually concluded that the relative movements of the Earth and Moon could not have resulted from it. The Earth would have been spinning too fast to account for its present rotation rate. The quest for an explanation of lunar creation continued, and a new theory would soon originate with an American. In 1909, Thomas Jefferson Jackson C. was a U.S. naval captain based at Mare Island near San Francisco. His official job was to keep the standard time for the U.S. West Coast. But C. was also a gifted scientist. As a young man, he had trained as an astronomer.
He was one of the first Americans to actually get a doctorate in astronomy. He went to Germany and got a PhD in astronomy, which was, almost unheard of back then. The U.S. was still scientifically total backwater in the 1800s.
C's duty station, Mare Island, had an observatory, and the captain's job allowed him plenty of time to theorize. He had spent time analyzing both the co-accretion and the fission hypotheses regarding the origin of the moon, and he wasn't convinced. Gradually, Thomas C. developed a completely different idea. It came to be called the capture theory. Essentially, C theorized that the moon had actually formed in a different part of the solar system from the Earth, that it orbited the sun just like the other planets, but that at some point it had moved too close to Earth and was captured by Earth's gravity.
His idea was that there's something that he called the resisting medium in outer space, which we know is not there now.
C never adequately explained what this resisting medium was supposed to be, possibly tiny particles of matter. Regardless, he was sure it no longer existed.
His idea is that for the Earth to capture the moon would have to come in from far away, and then it would hit this resisting medium and slow down, and then gradually get captured into an orbit. Maybe not at once, might take a little while, but gradually it'd be captured into Earth's orbit. It's a little bit like a bungee jumper jumping off a bridge. They'd go down, come back up, not quite as far, go down, come back up. And eventually they'd settle down at the bottom.
Thomas C's capture theory would certainly explain the difference in iron content between the Earth and the Moon. If the Moon formed elsewhere, its composition could be very different. On the other hand, the notion that Earth's gravity could capture and retain such a large object was unlikely, since there is no obvious resisting medium to slow down an object as big as the Moon. All three theories had significant weaknesses. The origin of the Moon remained a mystery. On On July 20th, 1969, U.S. astronauts set foot on the lunar surface for the first time.
It's one small step for man, one giant leap for mankind.
They had landed their lunar module on the hardened lava plain known as the Sea of Tranquility. And mission pilot Buzz Aldrin described the view as magnificent desolation.
Beautiful view. Isn't that something? Magnificent sight out here.
The astronauts brought back 48 pounds of moon rocks and dusty soil, or regolith.
Our position 1330, 6915.
Geologists at Johnson Space Center in Houston eagerly awaited their arrival.
The excitement when samples first came back was just electric. I mean, it was just incredible. Nobody really knew quite what to expect. And we realized right away that we had basaltic rocks, like one might see in Hawaii. In fact, very similar to rocks one would see in Hawaii.
The NASA geologists were intrigued to find not only basalts, but rocks of another sort. Rocks called breccias. Breccias form during asteroid impacts.
So if you can imagine a large impact body hitting the moon, is going to be very chaotic. It's going to throw up debris. Debris is going to come flying out of this, what winds up to be a crater after it's over, and you can see the many craters on the moon. This debris gets all jumbled up and lands on the ground around the crater, and then it gets compacted with the heat generated by the crater and gets turned into rocks that look very chaotic. You see all sorts of pieces in the rock of different sizes, different shapes, all pieces of the rock that were in the area that the impacting body impacted. We had just not seen anything like this on Earth.
The moon rocks soon began to tell a fascinating tale. First, the rocks and soil samples contained particles, indicating that the moon must have been covered by a deep ocean of lava after it formed. This notion was reinforced by the discovery that the rocks were lacking significantly in what scientists call volatile elements.
Volatile elements are those that can evaporate easily and therefore be lost when you heat up a rock. And some examples of volatile elements include water or potassium, for example. And if you compare the bulk Earth rocks to lunar rocks, you find that the lunar rocks are extremely parched. It's as if they've been heated and they've lost a lot of their volatile elements.
But along with these stark contrasts, the lunar samples also revealed at least one astonishing similarity between the lunar surface and rocks and soil from Earth.
The isotopes of individual elements, like oxygen in particular, you have different forms of oxygen. The moon had exactly the same ratios of different forms as the Earth did. But all the other rocks we knew from elsewhere in the solar system, which are meteorites that fall out of space, all have different oxygen isotope ratios, which tells you that the moon material and the Earth material are very, very similar.
In the end, the lunar samples had supplied a wealth of hard evidence regarding the geological makeup of the moon. But astronomers trying to understand the moon's origin were still left with a puzzle. For William Hartman of the Planetary Science Institute in Tucson, Arizona, the information gleaned from the moon rocks supported some ideas he'd been working on for nearly a decade. Now a distinguished astronomer and painter of space images, in the early 60s, Hartman was a graduate student at the University of Arizona, taking part in a project to map impact craters on the moon. From the enormous basins, or seas, to the smallest visible dimples.
We realized during this mapping in the 60s that the big basins are actually impact features. Very large asteroids hit the moon and made these huge explosions. Some of those are 600 miles across. How big an object does it take to do that? Something like 100 miles across. So we had large objects running around in the inner solar system as the Earth was forming, and they were crashing into planets.
For Hartmann, the notion that 100-mile-wide asteroids once impacted planets begged a couple of questions. Could planet-sized objects have ever collided? And could that have something to do with the formation of the moon? By 1972, Hartmann and fellow Tucson astronomer Don Davis had created a computer program to help them explore these ideas. The program made a rough attempt to simulate the accretion process in the early solar system. The astronomers wanted to see if any other planetary bodies formed near the Earth that could have crashed into it.
The idea was, if there was some other body there and it finally crashes into the Earth and blows off all this crustal material from the Earth, as well as from the impactor itself, maybe the moon could form out of that.
Sure enough, the simulation showed that a second planet could have formed in the Earth's accretion zone, one about the size of Mars. It wasn't the moon, because it had formed from the same elements as the Earth and should therefore have had the same iron core and heavy density as the Earth. The moon, of course, does not. That was evidence enough for Hartmann to formulate a new fourth hypothesis. It came to be called the giant impact theory. In 1974, a new hypothesis explaining the origin of Earth's moon debuted on the world's scientific stage. Its proponents dubbed it the giant impact theory.
The basic idea is that about 4.5 billion years ago, Earth collided with an object roughly the size of the current planet Mars. It's a very large collision, and it started the Earth spinning. It's what gave us our current 24-hour day, we believe. And this collision was so massive that it launched material into orbit around the Earth, and it's from that material that we believe the moon later coalesced.
Dr. Robin Canup and others at the Southwest Research Institute in Boulder have constructed a computer model to study the details of the giant impact scenario.
It divides up the Earth and this colliding rogue protoplanet into many different particles, and then the evolution of each particle is tracked through the course of the impact.
The simulation depicts the impact from a bird's eye view from the top down.
The Earth was probably partly molten even before this impact. So initially, the impactor came in from this direction. It hit the Earth with an off-center collision. And you can see the impactor has been stretched out into this long arm of material right here.
Scientists believe the upper layers of the Earth became completely molten following the impact.
The collision starts the Earth rotating. And you can also see that the collision has substantially distorted the shape of the Earth itself. After a couple hours, we see that this arm of impactor material has coalesced gravitationally into two large clumps. The inner clump of the impactor material is actually composed overwhelmingly of the impactor's core, so that when this inner clump recollides with the Earth, which happens right there, the vast majority of the iron that came in with the impactor is actually accumulated by the Earth. While this outer clump comes in and makes a close pass by the Earth and is stripped by the Earth's gravity into a long arm of material, which then breaks up to form this disk.
The material is thought to have coalesced to form the moon in less than a year following the massive impact. There is no sign of this impact on the Earth today, because at the time, our planet had only developed to about 90% of its current size. The remaining 10% would accumulate from later, much smaller impacts. Also, the Earth's own gravity had a reshaping effect.
Within a day after the impact, the Earth had reassumed a basically spherical shape, and any depression that the impact caused would have been smoothed over.
Giant impact theory originator Bill Hartmann presented his hypothesis at a scientific conference in 1974. But it received little attention for nearly a decade. Interest in the moon dropped off sharply at the end of the Apollo missions.
Yeah, beautiful. Very smooth. Very quiet ride.
Finally, at a lunar conference in Hawaii in 1984, 12 years after the last moonshot, the world's foremost astronomers reached a consensus. The giant impact theory was the most acceptable explanation to date for the origin of the moon.
I think there's still some people who say, okay, it's not really proven yet, but it's what I would call the default theory. If you look at any textbook of planetary science or geology, it's just the theory that's accepted. And there are certain small discrepancies which have yet to be explained, but by and large, it works.
Even with an agreed-upon theory of how our moon came to be, scientists have not finished studying our closest cosmic neighbor by any means. In fact, talk of returning to the lunar surface with a permanent manned outpost has recently emanated from the White House and NASA headquarters.
Gorgeous